Welcome. Today's story isn't about acceleration or autopilot. It's about factories, cash flow, long meetings, delayed shipments, and waiting for funding that might never arrive. This is how Tesla became a global tech empire, and how close it came to disappearing entirely. In the early 2000s, electric cars were an idea few people took seriously. The general consensus across the auto industry was that battery-powered vehicles had already failed. General Motors had cancelled its EV1 program. Honda had scrapped its electric offerings. Toyota was focused on hybrids, not full electric. Most Americans, if they thought about electric cars at all, pictured golf carts or underpowered experiments. Gasoline was cheap. Pickup trucks were selling well, and car culture, especially in the US, was still dominated by horsepower, chrome, and the thrum of internal combustion. But in a small corner of Silicon Valley, far from Detroit and even farther from the mindset of traditional auto manufacturing, two engineers were thinking differently. Their names were Martin Eberhard and Mark Tarpenning. Both had backgrounds in electrical engineering. Both had spent years in the tech world, building devices and products that, while unglamorous to the public, had moved technology forward. They weren't car designers. They weren't gearheads. But they understood energy storage, and more importantly, they understood scale, how small technologies could become big if the timing was right. They had sold their previous startup, Nouveau Media, for a decent sum, enough to think about what came next. And what came next, in Martin Eberhard's mind, was not software. It was a car. He had been watching the steady improvement of lithium-ion batteries. These were the same batteries used in laptops, phones, and portable devices. Over the past decade, they had become more reliable, safer, and slowly cheaper. And Eberhard began to wonder, what if you didn't try to reinvent the battery? What if you used the exact same cells found in laptops, thousands of them, bundled together, and built a vehicle around them? It sounded improbable, maybe even foolish, but he wasn't trying to compete with Toyota or Ford or BMW. He wanted to build something small, a low-volume, high-performance electric car, something sleek, expensive, and aspirational, something that proved electric cars could be exciting, not just efficient. They called the company Tesla Motors, named after Nikola Tesla, the eccentric inventor, visionary of alternating current, and near-mythical figure in the world of electricity. The name wasn't meant to sell cars immediately. It was meant to represent a kind of thinking, technical, historical, slightly rebellious. Tesla was officially incorporated in July 2003. In the earliest days, the company was little more than Eberhard and Tarpenning, a few laptops, and a set of spreadsheets. They had no factory, no design studio, no staff of automotive experts. But they had a theory that you could make an electric car work by adapting existing battery tech, and that the most practical way to bring it to market was to start at the top of the market, not the bottom. This was a reversal of most business logic. Conventional wisdom said, make it cheap, sell a lot, and scale. But cheap electric cars required cheap batteries, and cheap batteries did not yet exist. So instead, Tesla would build a sports car, something that could sell at a high price, even if it cost a lot to make. Something for early adopters, people who had disposable income, people who wanted to be part of something different. To build the car, they would need help. They couldn't design every part from scratch. So they approached Lotus, a small British car company known for lightweight sports cars. The plan was to use the Lotus Elise as a base, keep the chassis, modify the suspension, design a new body, and replace the gas engine with Tesla's electric drive system. This partnership was important. It gave Tesla a physical form to work with, something to test, something real, but the most important thing they needed was money. That's where Elon Musk entered the picture. By 2004, Musk was already wealthy. He had co-founded Zip2, sold it to Compaq, and gone on to help create PayPal. When PayPal sold to eBay, Musk walked away with over $100 million. He had already begun investing in other industries, most famously SpaceX, which aimed to build reusable rockets and lower the cost of space travel. Musk had an interest in sustainable energy, and he believed in electrification as a necessary step for the future. So when he met with Eberhard and Tarpenning and reviewed their plans, he agreed to invest. He didn't just put in money. He led the Series A round, investing $6.5 million and becoming chairman of Tesla's board. In public, Musk was not yet the face of Tesla. Eberhard remained CEO. Tarpenning handled technical operations. Musk provided oversight and vision, but over time, his influence would grow. With new funding, Tesla set up a small office in San Carlos, California. It was an industrial space, a few desks, a shop in the back for prototyping. Every square foot mattered. The early team was tiny, maybe a dozen people. They built battery prototypes by hand, ran early motor tests, wired systems manually, kept logs on whiteboards. There were no playbooks. No one had built a car company from scratch in the US in decades, much less one with no gasoline. Everything was trial and error. Each problem solved revealed to new ones. Thermal management, weight distribution, drive, feel, noise, wiring, vibration, charging interface, braking response, regulatory compliance, shipping, documentation, insurance, and the big one, cost, because every time they adjusted the design, it became more expensive, and by the time they showed off their first real prototype of the Tesla Roadster, the car was already over budget and behind schedule. The reveal happened in 2006. On the surface, it looked like a victory. The car was sleek, silent, fast, 0 to 60 in under 4 seconds, no emissions, and it looked nothing like a science project. It looked real, but under the surface, the situation was fragile. Tesla had no manufacturing line, no real supply chain, no distribution plan. The transmission being used in early models kept failing under stress. The battery packs were functional, but expensive and difficult to assemble. The final build cost of each car was higher than anyone had forecasted, and investors were starting to ask when deliveries would start. Tesla promised that production would begin in 2007, then 2008, then maybe a few units before the end of the year. Inside the company, tension grew. Eberhard was meticulous. Musk was impatient. Meetings became more difficult. Decisions were contested. Emails were longer. Days stretched into nights. The team kept building, kept testing, but the margin for error was gone. Eventually, in late 2007, Eberhard was removed. As CEO, a new executive, Michael Marks, came in temporarily, then Zeev Drury. But even with changes at the top, the fundamental problem remained. Tesla was running out of money. They had over 1,000 pre-orders for the Roadster, but they couldn't build the cars fast enough, and each one still cost more to make than it brought in. Musk began to take a more active role in day-to-day decisions. He poured more of his own money into the company. By some accounts, He personally funded payroll during the worst weeks. And then, in 2008, the global financial crisis hit. Investors froze. Capital markets dried up. Car sales plummeted. Banks collapsed, and Tesla came within weeks, maybe days, of shutting down. But at DIDN, not quite, in early 2008, Tesla was facing a problem it had seen before. But this time, the stakes were higher. They had a product, they had press, they had customers waiting, and yet, the company still did not have a reliable way to actually manufacture the Roadster at scale. The production plan was a patchwork of temporary fixes and improvisations. Lotus, their partner in the United Kingdom, was still building the base chassis. Tesla was modifying them in California with its own electric drivetrain, battery pack, and custom electronics. But this hand-built process was slow and fragile. Every step involved engineers correcting errors, adjusting components, and recalibrating systems. There was no automated line, no robotic assembly. Each vehicle was a near-custom job. And while early customers were enthusiastic, their patience had limits. Some had placed deposits 2 or even 3 years earlier. The original delivery date had slipped, then slipped again. By March 2008, only a handful of cars had made it into customer hands, and even those required constant support, software patches, and updates. Internally, the team was exhausted. Some employees were sleeping in their offices. Others were pulling 8 days. Tools were kept in toolboxes and in personal backpacks. Documentation was incomplete. Some of the vehicle systems were still being written in the final stages of testing. The cars were fast and quiet, but the infrastructure behind them was loud, messy, and precarious. One of the most persistent technical problems was the 2-speed transmission. The original plan had been to give the Roadster a gearbox that would allow for both quick acceleration and high top speed. But under the torque of the electric motor, the transmissions kept failing during durability tests. After multiple redesigns and supplier changes, Tesla finally decided to lock the car into a single gear, sacrificing top speed but gaining reliability. That was a pattern Tesla would repeat often in these years. Adapt, compromise, ship something that worked, but compromises alone could not save them from the broader financial reality. By the summer of 2008, the company's runway was shrinking. Tesla had already spent the majority of its Series B and C funding rounds. Musk had invested more of his own fortune, but it wasn't enough to keep the company stable. And then came the global crisis. In September 2008, Lehman Brothers collapsed. Markets froze. Tech companies began to issue layoffs. The auto industry braced for disaster. General Motors would eventually file for bankruptcy. Chrysler would too. Ford would barely survive. And here was Tesla, a young, unprofitable car company with a luxury vehicle no one had yet fully seen. Investors vanished. Fundraising discussions stopped. Term sheets were withdrawn. And inside Tesla, the future became very simple. Either find new money or shut the doors. On October 24, 2008, Elon Musk announced to the Tesla team that the company was out of cash. That day, Tesla laid off nearly a quarter of its workforce. About 90 people. The San Jose office was closed. Hiring was frozen. Projects were paused. The Roadster production line slowed even further. Then, just weeks later, Musk stepped in again, this time more decisively. He officially took over as CEO of Tesla Motors. It was not a title he had originally wanted. He had invested to guide the vision, to fund the company, not to run it day to day. But there were no alternatives left. The other CEOs had come and gone. The product was late. The money was gone. So Musk took the helm, and he put more of his own capital into the company, almost all of it. By the end of 2008, Musk had invested over $70 million of his own money into Tesla. Some weeks he was choosing which of his companies to fund, SpaceX or Tesla, because he did not have enough liquidity to keep both fully alive. As Christmas approached, Tesla was days away from bankruptcy. The company had barely enough cash to meet payroll. Suppliers were demanding payment in advance. The Roadsters already in production were sitting in shipping containers, waiting on final assembly, or still being debugged. Then, at the last possible moment, a lifeline arrived. On Christmas Eve 2008, Tesla closed a $40 million bridge round of financing, enough to stay alive into the new year. It wasn't a glamorous round. It didn't come from venture capitalists or banks. It came mostly from existing investors, many of whom doubled down simply to protect their original stakes. It was enough, just barely. Production resumed. The backlog of Roadster orders was slowly fulfilled, car by car. Every delivery brought a sigh of relief. Every customer who took possession of their car was another proof point. And as 2009 began, Tesla was still alive, smaller, leaner, but operational. Musk, now CEO, imposed a new style of management. He demanded speed, precision, and visibility. Weekly updates, engineering logs, rapid iteration. Delays were met with direct questions. Long meetings were reduced to sharp decisions. He was often in the office past midnight, sending emails, reviewing technical specs, asking about errors in spreadsheets. Some employees thrived under this system. Others burned out. The culture began to shift from scrappy startup to hard-edged mission company. It was not about survival anymore. It was about proving that Tesla could actually become more than a curiosity. The Roadster deliveries picked up pace. By early 2009, over 100 vehicles had been shipped. Still a tiny number, but it was the beginning of real revenue. Tesla set up service centers, built customer support systems, created owner documentation, held small events. Owners began posting online reviews. The public was seeing a real electric car on real roads. But the company was still bleeding money. The Roadster, even with its premium price tag, nearly $100,000, was expensive to produce, and Tesla had no other products. No cash-generating side business. No gasoline offerings. The plan had always been to start with a luxury car, then build a more affordable one. Now, the next phase needed to begin. In mid-2009, Tesla announced a partnership with Daimler, the parent company of Mercedes. The deal gave Tesla a $50 million investment in exchange for a small ownership stake and a battery supply agreement for Daimler's electric smart car. This was a turning point. It showed that Tesla could not only build a car, it could supply major automakers, and it gave Tesla new credibility in the automotive world, where few had taken it seriously. Later that year, Tesla also received a loan approval from the U.S. Department of Energy, a conditional commitment for $465 million, part of a federal program to support advanced vehicle manufacturing. These deals, combined with growing Roadster production and the public visibility of Elon Musk as CEO, gave Tesla something it had not had in years: breathing room. It was still risky, still hard, but the company was no longer running on fumes, and in the background, a small team of engineers was working on the next car, a sedan, all electric, not a $100,000 sports car, but something closer to the market average. A car that could be mass-produced, that could go head-to-head with traditional brands. It would be called the Model S. But first, Tesla would have to figure out how to build a factory, and how to build a company that could make not hundreds, but thousands of cars. In early 2009, Tesla was still delivering its first real product, Roadster, but each delivery was its own kind of logistical experiment. The cars were built in batches. No two were exactly alike. Some parts had to be adjusted in the field. Some had wiring differences. Some required software updates just weeks after being shipped. Each delivery was progress, but also feedback, and every bit of feedback meant another internal discussion, another tweak, another late-night engineering fix. At this point, there were still fewer than 200 Roadsters on the road, but the company was slowly moving forward. What was becoming clear inside Tesla was that building one car and designing the next were completely different tasks. The Roadster was, in many ways, a handcrafted vehicle, a modified Lotus, built in very small quantities, an early proof. But that model of production would never scale. Tesla knew this. The executive team knew it. The engineers knew it. And so, even while the Roadster was still mid-launch, another internal effort had already begun. They were starting to sketch the outlines of what would eventually be the Model S. At first, the idea of building their own car platform from the ground up seemed aspirational, maybe even too ambitious. They had no large factory, no global supply chain, no in-house press lines or stamping equipment. They had a prototype-level team used to building test parts by hand, not managing full-scale production. But Musk had made it clear, Tesla was not going to be a boutique automaker. It was going to become a real manufacturer, a major player. And that meant designing their own vehicle from scratch. In a small back room of Tesla's headquarters, a few early sketches were drawn. Long, low, a fastback design, for doors, all electric, a range of more than 200 miles. These early concepts were part design, fantasy, part engineering, challenge. What kind of cooling system would be required? Where would the battery pack go? How would weight be distributed? Would there be a front trunk, since no engine was needed? One of the central challenges was defining the skateboard chassis. The idea was simple in concept place. The battery pack flat along the floor of the car, underneath the cabin. This would keep the center of gravity low, improve handling, and free up space where the engine and transmission tunnel would have gone. But it had never been done at this scale. The battery needed to be safe in a collision. The wiring had to be redundant and heat managed. The pack needed a cooling system. And above all, it needed to be reliable over thousands of charging cycles. Tesla's battery engineers began testing different configurations. They used the same small format lithium-ion cells found in the Roadster, known as 18,650 cells. But now they would need more of them, thousands more, arranged in modules, managed by onboard software, kept at precise temperatures. Thermal runaway was a constant concern. A single damaged cell could overheat, and the heat could spread to adjacent cells. Engineers ran stress tests, punctured cells, overcharged them, monitored voltage decay. Every variable had to be understood. Meanwhile, a small design team began building interior mock-ups. The Model S would not be a cramped sports car. It needed to seat 5 adults comfortably, maybe more. There were conversations about jump seats, rear-facing child seats, storage capacity. Would the front trunk, what Tesla would later brand the frunk, be large enough to carry groceries? Would people understand what to do with it? The dashboard was debated. Would it use a traditional gauge cluster or something digital? Musk pushed for a fully digital driving interface. No mechanical dials, just screens. In 2009, this was unusual. Most cars still used analog speedometers and tachometers. Tesla began prototyping large touchscreen controls, not just for entertainment, but for climate control, navigation, and vehicle settings. Some called it visionary. Others called it impractical. But the team pressed forward, and as they did, another challenge became clear. Tesla had no place to build it. The Roadster had been assembled in a modified workshop, with final parts coming from the UK and multiple subcontractors. That approach would never work for a mass-market sedan. They would need a factory, a real one, with stamping machines, robotic welding arms, painting lines, inspection stations, shipping docks. A place big enough to build thousands of cars per year, tens of thousands. But in 2009, they did not have the money, or the workforce, or the experience. What they had was ambition, and time, a little. In these months, the internal culture at Tesla was shifting. The early Roadster, crew experimental, flexible, informal, was starting to give way to something more structured, more hierarchical. Roles were being clarified. Documentation was becoming stricter. Some early employees who had worn 5 hats were being asked to specialize. Some left, others adapted. Musk was everywhere. He reviewed slide decks late at night. He emailed questions with timestamps at 2:17 a.m. He reviewed cost projections, aerodynamics, weight targets. He asked for simulations. He pushed suppliers on timelines. He rejected design elements he thought were too conservative. He pushed the team not just to build an electric car, but to build the best sedan on the road, electric or not. The pressure was immense, but it was also focused. The Model S was not a side project. It was the future of the company. The Roadster, for all its importance, had always been step 1. Now they were building step 2, and step 2 had to work. During this period, the company also hired Franz von Holzessen, a former designer from Mazda and General Motors, to lead design efforts. He brought with him a broader understanding of production feasibility, surface, modeling, and what made a car not just functional, but appealing. Under Franz's direction, the Model S began to take shape visually. Smooth lines, flush handles, aerodynamic curves. It was not a car that shouted for attention. It suggested confidence, intention. But the production questions kept mounting. Tesla began searching for property, a space large enough to house their future factory. But real estate was expensive. Permitting would take time. Equipment would take longer. They explored partnerships. They evaluated contract manufacturing. They ran cost comparisons between new construction and repurposing existing plants. And all the while, they kept building roadsters. Some were now being shipped internationally. Others came back for upgrades. Owners loved the experience, but struggled with early software. Some chargers failed, others glitched. Service centers were limited. The company was hiring field technicians as fast as it could find them. Tesla had to walk both paths at once, deliver on the Roadster, and design and prepare for the Model S, which was at least 2 years away from production if everything went right. Inside the company, morale swung like a pendulum. Some days brought progress, others brought delays, an unexpected cost. a supplier pulling out, a prototype part failing inspection, a software build that crashed under load but slowly. The roadmap began to solidify. The Model S would be a four-door electric sedan with an all-glass panoramic roof, with digital instrumentation, with optional rear jump seats, with high safety ratings, with a single, flat battery pack beneath the floor. And if Tesla could find a way to build it, it would be the first car of its kind. But before they could build the car, they had to find a home for it. A place with high ceilings, wide doors, a history of metal and motion. They were looking for a factory, and soon they would find one in 2010. Tesla Motors was still a car company without a real factory. Roadster production was limited and fragmented. The chassis came from Lotus in England. Final assembly took place in a small workshop in Menlo Park. Battery packs were hand-built in a separate facility. Wiring was often customized. Quality checks happened wherever there was space. It worked for 500 cars per year. It would not work for 50,000. The Model S was moving from drawings and simulations into early mock-ups. Engineers were testing components. Designers were finalizing surfaces. Supply chain conversations were beginning. But there was no line, no conveyor, no stamping machines, no paint shop. Tesla needed a factory. Not a small one, a real one, preferably close to headquarters, accessible by road and rail, zoned for industrial use, already equipped for automotive production, and affordable. This was a tall order. Building a new plant from scratch would take years and hundreds of millions of dollars. Retrofits were risky. Existing factories were rare and usually in use. But in Fremont, California, an opportunity had quietly opened up. It was called NUMMI, the New United Motor Manufacturing, Inc. plant. NUMMI had been a joint venture between General Motors and Toyota. Originally opened in 1984, the site was massive, more than 5 million square feet of floor space. It sat on 370 acres. The plant had its own stamping line, paint booths, welding robots, loading docks, cafeterias, meeting rooms, and supply depots. For over 2 decades, NUMMI had been a success story. Toyota and GM had used it as a training ground for new manufacturing systems, especially Toyota's lean production methods. It had produced cars like the Toyota Corolla and the Pontiac Vibe at its peak. More than 5,000 workers filled its halls, but in 2009, as GM collapsed and Toyota reassessed its North American footprint, the plant had been shut down. The last vehicle rolled off the line in April 2010. Thousands of workers were laid off. The property sat quiet. When Tesla began exploring the site, it seemed almost too large for their needs. The entire company, at that point, could have fit into one wing of the facility. But Musk saw the potential, and the price was impossible to ignore. Because the factory had been closed, and no one else wanted it. Tesla acquired the NUMMI plant in May 2010 for just $42 million. That was a fraction of its original value. An industrial campus, previously operated by 2 of the world's largest automakers, was now under the control of a startup with 1 vehicle and no mass production experience. But acquiring a factory is not the same as operating one. Inside, the plant was dark, silent, equipment was idle. Cobwebs were gathering in corners. Fluorescent lights hung above conveyor belts that had not moved in months. Computers were unplugged. Office chairs were stacked against walls. Machines sat under plastic tarps. Pallets were half wrapped in torn film. Tesla began the slow work of making it usable again. Not all the equipment stayed. Some of it had been removed before the sale. Other parts were outdated, and Tesla did not plan to use all of NUMI's layout. They chose one section to begin outfitting, a section that would become the Model S. Assembly line. Engineers and operations managers walked the floor, clipboard in hand. They mapped workflows, noted ceiling heights, measured conveyor routes, took inventory of what systems could be salvaged and which had to be replaced. The size of the plant brought new challenges: lighting, HVAC safety signage, access control, water lines, drainage, bathrooms, electrical loads, Wi-Fi coverage, emergency exits, forklift routes. It all had to be reviewed, approved, logged, and inspected. Tesla was no longer modifying small parts in a warehouse. They were standing inside a machine built for tens of thousands of cars per year. The company began to hire welders, painters, facilities, technicians, former NUMI employees, new recruits from other industries. Some came from aerospace, some from other automakers, some from the local area. Hiring was slow, training was slower. Everyone had to learn the new vehicle platform, the battery pack configuration, the assembly sequence. Software engineers wrote tools to track assembly timing. Procurement teams began negotiating with vendors. Layout planners designed workstations. Safety officers walked the floor and marked trip hazards. Managers reviewed labor schedules. Everything from coffee availability to restroom access was now a logistics question. And then there was the equipment, the stamping press, the robotic arms, the paint line, the torque tools. Everything had to be tested, calibrated, commissioned. Tesla began ordering parts months in advance. Crates arrived with machinery from Europe. Forklifts moved steel frames into position. Electrical panels were upgraded. Paint booths were sealed and pressure tested. The facility became a live construction zone. Tesla still had only one model, the Roadster. But now they had a campus that could build thousands of vehicles. The scale was intimidating. The Model S would require thousands of parts, hundreds of workers, and precise timing across dozens of stations. To help finance it all, Tesla pursued something bold, an initial public offering. In June 2010, Tesla Motors became the first American car company to go public since Ford in 1956. The IPO raised over $200 million. It gave the company new liquidity, and it gave Elon Musk and his team a new challenge: quarterly expectations, public reporting, shareholder questions. Tesla was now a public company, with a nearly silent plant, and a sedan that did not yet exist. But they had blueprints, they had staff, they had tools on pallets, waiting to be installed. They had conference rooms with whiteboards covered in schedules. They had boxes of wiring harnesses stacked beside test benches. They had a plan, and inside a corner of the Fremont plant, the first pieces of the Model S production line were coming into place. But even with space and funding, building a factory is not the same as building a car, and the real test was still to come. By the middle of 2010, Tesla Motors had something they had never had before: space. The former NUMI plant in Fremont now belonged to them, though only in part. The entire facility was far larger than Tesla's needs at the time. But within one portion of the vast industrial shell, the earliest traces of a real car company were taking shape. But the task ahead was not as simple as turning on machines and pressing a green button. Tesla's situation was unusual. Most car companies already had decades of institutional knowledge, playbooks, manuals, legacy systems. Tesla had to invent its production methods while still defining the vehicle they were trying to build. This meant the production line and the product itself were being designed in tandem. Every change to one caused ripples through the other. The Model S was not a simple vehicle. From the outset, it had been envisioned as both a technological showcase and a practical luxury sedan. It would be larger than the Roadster, able to seat 5 adults, or 7, if you counted the optional rear-facing jump seats. It would include a large touchscreen, a fully digital dashboard, and would be built around a completely flat battery pack, integrated into the floor of the vehicle. This required a very different assembly strategy at most automakers. The vehicle is built around a central chassis, a steel frame that becomes the skeleton of the car. Components are attached in sequence as the body moves down the line. Tesla, however, had to figure out how to build a chassis that doubled as a battery housing, a crash structure, and the base for a new kind of powertrain. The first challenge was battery module integration. The pack would consist of thousands of small cylindrical cells, similar to laptop batteries, grouped into modules, managed by software, and cooled with liquid channels. These modules had to be assembled, tested, installed into the main pack housing, and then married to the rest of the car. That meant building a battery production line inside the factory. Tesla had never done this at scale before. Each module required specific thermal paste, precise spacing, proper cooling line routing, and fault checking. Misaligned cells could cause shorts. Over-tightened bolts could crack casings. Every torque setting mattered. Even once the pack was assembled, it had to be hoisted into position and attached to the car body during final assembly, a step that required sub-millimeter alignment and heavy lifting equipment. Above the battery, Tesla's designers had laid out the Model S cabin with a fully digital interface, flush-mounted touchscreen, a minimalist dashboard, and an open-feeling interior. It was ambitious. But for production staff, it meant managing complex wire harnesses, software updates, and panel alignment. Tolerances more commonly found in luxury vehicles. One of the most intricate systems was the door handle mechanism. The Model S featured flush door handles that extended when touched. It was sleek, distinctive, and prone to issues. Each handle required a small motor, a sensor, and a logic controller. If one wire was misrouted or one sensor misaligned, the handle might fail to deploy. If the weather was too cold or too wet, early prototypes stuck. But design changes could not always be made in isolation. A door handle revision might affect the door skin, which affected the door stamping, which impacted the tooling that made the panels, which delayed the supply order, which pushed the timeline back. Tesla had to begin learning what traditional automakers had already internalized, that design, engineering, and manufacturing are all bound together in a system of dependencies, and every late decision upstream caused delays downstream. The Model S assembly line was divided into key zones. First, body shop, where stamped metal panels were welded together by robotic arms and human workers into the vehicle's structural shell. Tesla had to commission new welding robots, train operators, and calibrate each weld sequence, spark shielding, joint placement, cooling times, weld strength testing. Next, paint shop, a critical area that few visitors ever saw. The Model S needed a high-end finish. Tesla wanted deep, lustrous colors with multiple clear coats. Paint chemistry had to be tested for environmental compliance. Spray booths required precise air filtration. Overspray had to be minimized. Robots learned spray paths over hours of trial runs. Then came general assembly, where glass, wiring, seats, carpet, center consoles, and the 17-inch touchscreen were all installed. Here, the human element returned in full. Each workstation had defined tasks, but Tesla's process was still evolving. Workers gave feedback, tools were adjusted, tasks were reordered for ergonomics. If one wire harness came in too stiff, it might slow down 3 different assembly stations. Throughout this, Tesla had to meet regulatory requirements. Crash testing was mandatory. The Model S needed to meet US safety standards for frontal side and rear impacts. Tesla built crash test mules, loaded them with sensors, and sent them to controlled collisions. Each test was expensive. Each failed test meant redesigns, adjusting crumple zones, reinforcing pillars, rethinking restraint systems, and then there was supplier management. Tesla had relationships with dozens of vendors for aluminum panels, electronic components, sensors, switches, adhesives, fabrics, rubber seals. But suppliers were cautious. Tesla was still unproven. Some hesitated to scale up production. Others raised prices. Some parts arrived late or out of spec. Quality engineers inspected shipments daily. Rejected lots were quarantined. Production had to shift to accommodate shortages. As Tesla refined the line, they also began pilot builds. These were early production cars, assembled to test the flow of the line. They were not for sale. Each pilot build revealed new issues: trim that didn't fit, fasteners that stripped, software that froze, doors that rattled. Every fix was documented. Teams met to prioritize repairs. Change orders were issued. Line workers were retrained. The process restarted. And looming over all of this was the promise of a 2012 delivery. Tesla had publicly stated that the first Model S units would reach customers in mid-2012. That date was now less than 2 years away. Internally, the schedule was slipping. But Tesla did not have the luxury of delay. Investors were watching. Analysts were skeptical. Media was paying attention. Elon Musk made frequent visits to the factory floor. He asked questions about cycle time. He reviewed toolpaths. He watched panels being aligned. He critiqued panel gaps. He tested the software build in demo vehicles. He gave feedback on font size, on the touch response of the screen, on the sound of the door closing. He slept at the factory during key weeks. His intensity shaped the culture. Speed mattered. Details mattered more. Yet for all the pressure, there was progress. The line began to move faster. Errors decreased. Teams communicated more smoothly. Pilot builds improved. Quality checks became routine. Suppliers stabilized. The paint shop reached full operation. The first final assembly Model S vehicle rolled silently to the end of the line and passed inspection. Not for sale, not yet, but built in the factory Tesla now owned. A car built from scratch, on a line they had created, in a plant that had once been abandoned. And for the first time, they had proof that mass production was within reach. But now came the hardest part. Scaling that process from 1 car per week to hundreds, and convincing the world that Tesla was no longer an experiment. By early 2012, Tesla's Model S assembly line was no longer theoretical. The building blocks were in place. The stamping tools were tuned. The paint shop was running full cycles. The robotic welders had been programmed and reprogrammed, and the final assembly teams had rehearsed their motions hundreds of times. But building a car is one thing. Delivering it is something else entirely. Inside the Fremont plant, the process of pre-delivery ramp-up was underway. Tesla began assembling release candidate vehicles cars that were no longer hand-built prototypes but not yet for sale. These vehicles were as close as possible to production spec, and they were tested obsessively. Every door latch, every motor controller, every climate system cycle. These cars were subjected to cold soak tests, heat cycle simulations, charging tests, range validation, and emissions-free certification. Each car underwent what Tesla called end-of-line validation. That meant a full electrical inspection, connection, checks on every harness, screen functionality, software install, drive test on the internal track, brake responsiveness, suspension calibration, even things like glove box light behavior and speaker output were logged. Every data point collected fed back into an internal loop of refinements. It was slow, but it was moving. Behind the scenes, Tesla's logistics and delivery teams were preparing for something new. For the first time, Tesla would be delivering hundreds of vehicles to retail customers, not small batches of roadsters to early adopters. These customers were not all in California. They were spread across the country, and Tesla had very few retail or service locations. The company had made a decision early on that set it apart from traditional automakers. No dealerships. Tesla would sell its vehicles directly. It would manage its own service network, handle customer contact itself, maintain end-to-end control. This decision, while strategic, created complexity. No dealership network meant Tesla had to open its own galleries and delivery centers, hire and train its own service technicians, and develop its own parts, logistics, systems. And as the first real delivery date approached, every part of that system had to work. The official launch event for the Model S was scheduled for June 2012 inside the factory. A select number of customer vehicles, low VIN numbers, often belonging to early investors or high-profile pre-order holders, were being finalized. They were checked, double-checked, detailed, and polished. Staff were instructed to treat these as milestone vehicles, not just cars, but representations of the company's work over the last 4 years. Each panel gap was measured. Each software build was flashed and reflashed. Interior trim alignment was scrutinized. Quality assurance reports stretched dozens of pages. On June 22, 2012, Tesla held its first Model S delivery event at the Fremont factory. It was modest. As far as automotive launches go, the production line served as the stage. Musk gave brief remarks. Engineers and early employees stood in the background, watching. Then, one by one, the first Model S cars were handed over to their owners. Photos were taken. Applause followed. Outside, the media coverage was polite but cautious. The car was real. It existed. It drove well. But the question wasn't whether Tesla could build a few hundred Model S sedans. The question was whether it could build thousands every month with consistent quality and support them long after the sale. Because delivery is not the end of the process. It is the beginning of a long commitment. Within weeks, more Model S units began to roll off the line. Tesla ramped production carefully. At first, only a few dozen per week. Then more. Engineers monitored the line constantly. Early customer feedback was reviewed daily. Issues were logged. Service requests were tracked manually. There were glitches. Some door handles malfunctioned. Some screens froze. Some early units had software issues that required factory-level fixes. Tesla had very little buffer. Every car sold brought in revenue. Every mistake risked damaging reputation, and supporting these vehicles required new layers of infrastructure. Tesla began expanding its service, network hiring mobile technicians, renting service bays, even sending repair teams to customer homes or workplaces. They began training Tesla Rangers, technicians who traveled with diagnostic tools and parts to address issues on site, often within hours of a request. At the same time, the company worked to improve its remote diagnostics. The Model S was designed to be connected at all times. Through internal logging systems, engineers could track battery health, software anomalies, charging behavior, and even driving patterns, allowing Tesla to fix bugs remotely, schedule maintenance preemptively, and push over-the-air software updates directly to vehicles. This was new in the automotive world. Most car makers relied on service appointments, recall notices, or local technicians. Tesla used code. Updates were queued, bug fixes were tested, packaged, and deployed. Customers would wake up to new features, new interfaces, and performance improvements without visiting a shop. This was a selling point, but it was also a risk. Every update had to be rigorously tested. A software glitch could impact thousands of cars overnight. As the fleet grew, Tesla's internal software QA processes expanded. They built simulations, used test benches, deployed phased rollouts, and still, occasionally, things went wrong. Meanwhile, the Fremont plant was growing busier. Suppliers were shipping larger batches. Production managers worked in shifts. Weekly output goals were posted on whiteboards. Bottlenecks were analyzed. A single missing part, sometimes a fastener or gasket, could delay dozens of builds. Tesla implemented parts tracking systems, created escalation protocols, hired more logistics staff. Every Friday, internal meetings reviewed metrics, units built, defects per vehicle, customer delivery, wait times, service turnaround, component failure rates. The Model S was no longer a goal, it was a product, and like all products, it had to meet expectations. In the second half of 2012, Tesla delivered over 2,400 Model S units, a small number by industry standards. But for Tesla, it was transformational that they now had real revenue, repeat customers, referrals, media interest, analysts writing long notes about margins, battery costs, unit economics, and factory throughput. Inside Tesla, attention was already shifting forward, toward expanding the lineup, toward global markets, and toward what came next. But for now, the company had one goal: keep the line running. Every hour. Every day. Without fail. By the final quarter of 2012, Tesla Motors had moved out of the conceptual phase and into what every car company eventually encounters: the long middle stretch. It was no longer about whether they could build a car. It was about whether they could build many of them, consistently, at quality, while reducing cost. The Model S was being delivered in growing numbers. Tesla had reached a modest but steady rate of around 400 vehicles per week by the end of the year. Each unit represented a real customer, a real financial transaction, and a real post-delivery obligation. The cars were being tracked, reviewed, written about, compared, and like all new products, they were being stress-tested in the most unpredictable environment possible: real life, across California, Oregon, and a handful of other early launch states. The first Model S owners began to report small but telling issues. Some problems were mechanical: creaks in the sunroof assembly, uneven trim around windows, a slight misalignment of interior panels near the dashboard's edge. Other problems were electronic: touchscreen lags during cold starts, Bluetooth pairing inconsistencies, firmware updates that temporarily disabled backup camera views, in rare cases, full software freezes, requiring hard resets. Then there was the now famous door handle problem. The flush-mounted handles on the Model S were visually striking. They sat hidden in the door skin and extended outward when touched. But each one contained a small motor, a gear mechanism, a sensor, and a logic board. If any part failed, the handle could jam, or refuse to present, or extend but not retract. In some cases, customers were locked out entirely. Tesla's engineering teams knew about the issue. They had been monitoring it since the pilot phase, but the failure rates were now statistically visible. Data flowed in daily. Field service teams returned with photos, logs, repair notes in some weeks. More than 5% of delivered Model S vehicles experienced door handle problems. The company began to react. A redesign was initiated. The internal mechanism was re-engineered to reduce stress on the motor. The sensors were recalibrated. The firmware was updated. The design change was integrated into the production line, and retrofit kits were shipped to service teams. Early adopters were invited for free replacements. It was a minor issue, technically speaking, but it illustrated the broader reality. Tesla was now supporting a fleet. This meant warranty tracking, part replacement logistics, field technician routing, customer communication, service appointment, scheduling, internal audit trails. The company had to mature quickly, and at the same time, it had to lower costs. The Model S, even at its luxury price point, had very thin margins in the early months. Tesla was paying high prices for components due to small batch ordering. Some parts were still being hand-assembled. The complexity of the vehicle's design, the large touchscreen, the fast acceleration, the configurable powertrain made it expensive to build. Elon Musk began pushing hard for cost-down projects. Each department received targets: reduce manufacturing waste, increase part reusability, negotiate supplier discounts, simplify assembly steps. Engineers were assigned to investigate why specific tools took extra time, or why a part required manual alignment, or why a software function needed 3 button presses instead of 1. The battery pack, the most expensive single component, was an early focus. Tesla worked with Panasonic, its primary battery supplier, to improve cell consistency. Small changes to chemistry, insulation, and packaging were tested. Assembly jigs were redesigned for tighter tolerances. Cooling loops were rerouted to reduce the number of welds. Anything that improved yield was considered valuable. At the same time, the company's customer base was expanding. Tesla had originally prioritized deliveries within driving distance of its California base, where service coverage was easiest, but now deliveries were occurring across the United States. Vehicles were being shipped to the East Coast, to Texas, to Florida. And with each delivery came a new logistical challenge: service access, charger availability, regional compliance. Tesla responded by opening more service centers and deploying additional mobile technicians. It hired staff in key metropolitan areas, leased small garage spaces, shipped diagnostic tools, created proprietary training modules for technicians. Everything was built from scratch: the service uniforms, the internal ticketing software, the response time targets, and the company's next frontier was already being prepared. Tesla had long advertised that the Model S could drive long distances on electricity alone. but the charging infrastructure did not yet exist. Public chargers were rare, slow, and often incompatible. Tesla decided to build its own network. The supercharger program began quietly. In September 2012, Tesla unveiled the first 6 stations, mostly located in California. Each could deliver significantly more power than traditional Level 2 chargers, allowing Model S owners to regain a large portion of their range in under an hour. The launch was strategic: limited sites, controlled access, all within high-traffic corridors. But the vision was broader: a continental network of fast chargers, available only to Tesla drivers, designed specifically for long-range electric travel. The plan was bold, costly. It required real estate deals, construction permits, high-voltage electrical work, utility coordination, but Tesla believed it was essential. The company knew that most daily driving could be done by home charging, but long trips, the kind that defined how Americans perceived vehicle utility, were the gap, the pain point. The early superchargers were free to use for Model S owners. They became part of the vehicle's value proposition, an infrastructure perk, and a public symbol. Each charging station included a small Tesla logo, a minimalist design, a glowing red accent, and a feeling, at least among early adopters, of being part of something new. Meanwhile, inside the Fremont plant, production lines were evolving. Cycle times were improving, tool changeovers were faster, scrap rates were falling. Floor supervisors reported fewer stoppages. Tesla upgraded parts of the line with new robots, expanded storage areas, and implemented real-time dashboards that tracked performance on screens visible to every station. It was still hard, still manual in many places, still far from smooth, but the difference between the line in June 2012 and the line in December was visible, tangible. Tesla ended 2012 having produced about 2,950 Model S vehicles. The ramp had been slower than some expected, but it had occurred, and the foundation had been laid. In 2013, the focus shifted again, from simply surviving delivery to building scale. This meant increasing output to thousands of vehicles per month, managing inventory, handling trade-ins, preparing for international expansion, and beginning to tell a new story. Not just that electric cars were real, but that they could compete. The year ahead would test Tesla's ability to operate at volume, and every new customer raised the same question: could this company really keep up? Tesla entered 2013 with momentum but little margin for error. The company had delivered a few thousand Model S units in the final months of 2012. Enough to demonstrate viability, but not yet enough to satisfy financial analysts, investors, or its own internal forecasts. The factory line at Fremont was running, but still maturing. Production was now a daily exercise in coordination, not theory. Every morning, department leads across stamping, welding, paint, assembly, battery, and testing reviewed the previous day's output. Metrics were broken down into hourly data: number of vehicles started, number completed, issues found, time lost, parts short. Each category had a team responsible, and in many cases, issues came not from lack of planning, but from the sheer complexity of scaling. The welding robots that joined, the aluminum body panels had to be recalibrated constantly. Aluminum was lighter and less forgiving than steel. Slight shifts in temperature or tool wear could result in welds that looked fine but failed inspection. Tesla's quality assurance teams ran ultrasonic tests. They monitored internal faults, logs, failed welds, meant body shells had to be pulled from the line, repaired manually, and retested, adding hours to a process that was already running on tight cycles. In paint, temperature and humidity controls were critical. The multi-layer paint process required each layer to dry to specification before the next coat could be applied. Early in 2013, Tesla had trouble with specific colors. Red and pearl white required more precise application techniques, and rework rates were higher. Small bubbles or uneven gloss could lead to full panel repainting. Customers expecting luxury-grade finishes had little tolerance for defects. Despite these challenges, Tesla's production volume increased steadily. By March 2013, the company had achieved its target of 400 vehicles per week, and by the middle of the year it was approaching 500. That translated to over 20,000 vehicles annually, a scale that many in the industry had once considered unreachable for a new manufacturer, let alone one building electric vehicles from scratch. And the financial picture began to shift. For the first time in its history, Tesla posted a quarterly profit in Q1 2013. It was modest, just $11 million in GAAP net income, but symbolically important. Tesla was no longer burning money on pure R&D. It was now earning income from operations. Shareholders took notice. Tesla's stock began to rise. Analysts revised their projections. Media coverage turned curious. The company used this moment to announce an expansion of the supercharger network. Previously, superchargers had been confined to a few corridors in California and the Northeast. In May 2013, Tesla unveiled plans to triple the size of the network within a few months and expand to cover the entire continental United States by the end of the following year. This meant new installations every week. Tesla negotiated with property owners, often shopping centers, rest stops, or highway-adjacent parking lots, to host the stations. Each site required electrical upgrades, concrete work, charger installation, branding, and maintenance planning. Unlike gas stations, superchargers did not have attendants. They were meant to be quiet, self-managed locations, places where Tesla drivers could plug in, charge for 30 to 40 minutes, and continue their journey. Each new location was mapped in the vehicle's navigation system. Drivers could route long trips using Tesla's software, which would automatically plan charging stops based on remaining battery range and location behind the scenes. Tesla's energy and charging division worked on monitoring. Each supercharger reported its status: available, in use, offline, back to a central network. If a charger failed or lost connectivity, Tesla's service team could dispatch a technician. This level of integration gave Tesla control no other automaker had. As more customers began to rely on long-distance travel, Tesla also expanded its customer support infrastructure. A call center was built out. Service policies were clarified. Tesla created a vehicle trade-in program, which allowed customers to exchange older vehicles, including non-Teslas, for credit toward a new Model S. Meanwhile, inside the Fremont plant, continuous improvement efforts were underway. The company introduced lean manufacturing practices originally developed in Japanese automaking, focused on minimizing waste, maximizing efficiency, and creating a culture of constant, small refinements. Managers walked the floor, interviewing line workers. Notes were taken on which tools were slow, which fasteners were difficult to reach, which motions caused fatigue. Workstations were adjusted, heights were modified, parts bins were moved closer, screws were replaced with clips. Wherever a process could be simplified without sacrificing quality, it was. Tesla also began vertical integration experiments. Traditionally, automakers outsource significant portions of their vehicle components. Tesla was increasingly interested in making things in-house. It acquired small suppliers, built new tooling, expanded its battery line. Some critics saw this as a risk, others saw it as long-term strategic control. Customer feedback played a growing role in vehicle updates. Tesla monitored forums, emails, service logs, and internal tickets. When drivers reported software glitches, navigation lag, display reboots, false warnings, Tesla bundled fixes into software patches. These were pushed to the fleet remotely, sometimes overnight. It was a cycle that blended product development with ownership experience, and the Model S itself began to evolve. In June 2013, Tesla introduced the Model S Performance Plus package, offering improved suspension, updated stabilizer bars, and enhanced dampers for better handling. Later that year, dual-motor all-wheel drive variants were announced. Software updates improved charging speed, navigation interface, and driving dynamics. Tesla was not just building a car. It was maintaining a platform. And quietly, within internal meetings and slide decks, the company began laying plans for what came next. The Roadster had proven that electric cars could be fast and exciting. The Model S had shown they could be luxurious, practical, and desirable. But Tesla's stated mission was broader: to accelerate the world's transition to sustainable energy. That meant building a mass-market vehicle, smaller, more affordable, simpler to produce. Early discussions centered around price points: a vehicle starting around $35,000, a range of more than 200 miles, a 5-seat configuration, all built on a next-generation platform. Some internal teams referred to it as Gen 3. Others began to use what would become its eventual name, Model 3. But Tesla was still years away from producing it. Before then, they would need more battery capacity, more production space, better automation, more suppliers, more capital. The year 2013 ended with Tesla having delivered over 22,000 Model S vehicles, expanding its global footprint, building dozens of superchargers, and setting its next milestone in motion. The company had crossed the threshold into stability, but staying there would require something it had not yet achieved: true manufacturing efficiency at scale. And the next chapter would be focused not on dreams, but on discipline. By early 2014, Tesla had reached an important inflection point. The domestic rollout of the Model S had gone from tentative to stable. Service centers were growing in number. Supercharger corridors were being stitched across highways like charging arteries, and production in Fremont was steadily increasing. Now came the next inevitable question: what happens when the cars have to leave the country? Tesla had always planned to be a global automaker. Electric vehicles were a worldwide issue. Emissions and fuel consumption were not isolated to the United States. But actually selling cars internationally involved a long list of obstacles, many of which were new to Tesla's leadership and engineering teams. Tesla began with Europe. Europe was seen as a strong target market for electric vehicles. Several countries offered generous incentives, fuel prices were higher than in the US, and the general public was more open to smaller, more efficient vehicles. Moreover, many European governments had already begun implementing low emissions zones and congestion charges that favored electric drivetrains. But Europe was not a single unified market. It was a patchwork of regulations, vehicle standards, taxation systems, and customer expectations. The first major hurdle was type approval. Unlike in the US, where vehicles are certified for sale by the Federal Department of Transportation and the Environmental Protection Agency, European vehicles must go through the European Union Whole Vehicle Type Approval WVTA system. This required Tesla to submit vehicles for crash testing, emissions validation, even though electric vehicles emit no tailpipe gases. Certain certifications were still required: pedestrian safety compliance, lighting standards, and electronic interference regulations. Tesla engineers had to adapt the Model S to comply with EU requirements. That meant adding features like rear fog lights, adjusting headlight beams for left-hand and right-hand driving markets, incorporating the correct warning labels in multiple languages, and ensuring that all onboard systems met the EU's electrical interference guidelines. Even small differences, like the color of the turn signal indicators or the icon shown on the dashboard for open doors, had to be corrected to avoid failing inspection. Once these hurdles were cleared, Tesla faced its next operational challenge: logistics. The Model S was assembled entirely in Fremont. To reach Europe, vehicles had to be shipped across the Atlantic, typically via cargo vessels leaving from California ports. These ocean voyages could take several weeks, and any delays in port customs, processing, or last-minute paperwork issues could create bottlenecks. Once the cars arrived, they had to be offloaded, transported to regional distribution centers, inspected for shipping damage, and prepped for delivery. In the US, Tesla was already controlling its own delivery process. In Europe, it had to quickly replicate that structure from scratch. This meant hiring staff, leasing or building delivery hubs, and setting up service centers in major urban regions. The first deliveries in Europe began in Norway. Tesla chose Norway strategically. The country had one of the highest rates of electric vehicle adoption per capita in the world. The Norwegian government offered a generous package of incentives: no import taxes on electric vehicles, exemption from VAT, free toll road usage, free municipal parking in many cities, and access to bus lanes. The Model S quickly became popular in Norway. Tesla held delivery events. Customers shared experiences on forums and social media. The supercharger network, which had started in California, now made its first leap to continental Europe. Tesla installed chargers along Norway's major highways, connecting Oslo to other major cities. From Norway, Tesla expanded outward. The Netherlands, Germany, Switzerland, and the United Kingdom were next. In each country, Tesla had to negotiate real estate for retail spaces and service centers, secure permits for charger installations, and navigate each country's version of automotive sales regulation. In the Netherlands, Tesla established a European logistics and assembly point in Tilburg. This location became a crucial piece of Tesla's European puzzle. Rather than shipping fully built vehicles from the US, Tesla shipped partial assembly vehicles without battery packs from Fremont to Tilburg. The vehicles were reassembled with battery modules and finalized for delivery. This offered several benefits. It allowed Tesla to avoid certain import tariffs by classifying the vehicles differently under customs law. It also gave Tesla a European base for repair operations, part distribution, and final vehicle inspection before delivery to customers. The facility included a small test track where every reassembled car was driven for validation. Meanwhile, Tesla faced a different kind of challenge in Germany. Germany was home to the world's most well-known automakers: Mercedes-Benz, BMW, Audi, Volkswagen. These brands had deep customer loyalty, wide service networks, and powerful lobbying influence. German automotive media were skeptical of Tesla. Reviewers praised the Model S's acceleration and technology but questioned its build quality and long-term reliability. Tesla responded with outreach. Elon Musk visited Germany, gave interviews, and publicly committed to expanding service coverage. He announced the opening of more superchargers and additional service centers across the country. The company even offered test drives to journalists and policymakers, but Germany also exposed a new set of expectations. German drivers were accustomed to precise handling, refined interior materials, and detailed fit and finish. The Model S delivered impressive performance, but sometimes lacked the tactile polish of a Mercedes E-Class. Tesla began quietly making hardware improvements, tighter tolerances on interior panels, upgraded materials in later builds, improved sound insulation, and revised suspension settings for European roads. At the same time, Tesla began working toward entry into China. China represented an enormous market potential, but also one of the most complex regulatory environments Tesla had yet faced. The Chinese government encouraged electric vehicle development, but foreign automakers were typically required to form joint ventures with local companies to manufacture and sell vehicles domestically. Tesla did not want to enter a joint venture. It wanted full control over its branding, software, and service model. So initially, Tesla chose a limited entry strategy: export fully built vehicles from the US, sell them through Tesla One stores in major cities like Beijing and Shanghai, and begin building brand awareness. Even this modest start involved significant effort. Tesla had to ensure that its software supported Chinese character sets. Charging standards had to be adapted to Chinese grid conditions. Maps, navigation, voice recognition all required localization. Tesla also had to comply with Chinese regulatory bodies for vehicle importation. Emissions compliance again, for labeling and bureaucratic purposes, and tax classification. Meanwhile, customer expectations in China were unique. Buyers wanted luxury features, strong brand cachet, and responsive after-sales support. Tesla began recruiting bilingual sales staff, hiring local service technicians, and working to overcome skepticism about battery longevity in harsh climates. Back at headquarters, Tesla's operations teams were now maintaining a global distribution map. Dozens of countries, hundreds of routes, thousands of vehicles. Inventory systems had to be updated to track not just where a car was in the factory, but where it was on a ship, in customs, in delivery prep, or in a service bay. Regional differences had to be tracked: power adapters, license plate frames, regulatory stickers. By the end of 2014, Tesla had delivered vehicles to over 30 countries, built superchargers across Europe and parts of Asia, and established itself as an actual global automaker. Not just a startup with overseas customers, but a company with physical infrastructure, real estate, staff, and a working support network on multiple continents. It had taken years to reach this point, and still, Tesla knew this was only a foundation. The Model S was a success among early adopters, but to reach mass-market volumes, Tesla would have to do more than build fast sedans and ship them overseas. It would need a true product portfolio, and behind the scenes, a new vehicle was already in development. When Tesla first announced the Model X in early 2012, it was presented as a natural extension of the Model S platform. A larger vehicle, better suited for families, with higher ground clearance and more cargo capacity. But at its core, it was supposed to be relatively straightforward. The same battery pack, same electric motors, similar chassis, That assumption would not hold. From the moment the design team began exploring what the Model X could be, the ambition escalated. Elon Musk personally pushed for the SUV to be unlike anything else on the road. It could not be a standard crossover with an electric drivetrain. It had to be visually unique, technologically advanced, and instantly recognizable. That's where the idea of the Falcon Wing doors came in. The Falcon Wing doors, not to be confused with traditional gull-wing doors, were double-hinged and motorized. They were designed to open upward in a tight arc, requiring less lateral space in crowded parking areas. They were futuristic. They were also extremely complex. Each door contained multiple sensors to detect nearby obstacles, walls, ceilings, other cars, and would adjust its opening arc accordingly. Inside each hinge assembly was a set of custom-built motors, actuators, and controllers. The doors had to operate smoothly in heat, cold, rain, snow. They had to remain safe during crashes, and they had to pass every federal safety regulation governing egress and roof structure. No other automaker had built anything like them for a mass-market production vehicle. Tesla committed anyway, and the Falcon Wing doors were just one element of the Model X's expanding complexity. The front windshield was enlarged into a sweeping panoramic glass dome that extended over the front seats, requiring new glass sourcing, new defogging systems, and extensive structural reinforcements. The rear seating used monopost second-row seats, each mounted on a pedestal, offering a modern look but making folding and cargo loading more difficult. Tesla wanted the Model X to seat 7 adults, have all-wheel drive, a large battery pack, and performance that rivaled sports sedans, all while maintaining a low drag coefficient, high safety standards, and the same minimalist interior design language introduced with the Model S. By 2013, engineers were beginning to voice concerns. Each design choice was interesting on its own, but in aggregate, they were causing severe integration problems. Many components had no off-the-shelf equivalent. The doors alone required months of custom software development just to handle obstacle detection and motion logic. Testing the motor assemblies revealed failures in cold climates. Sensors interfered with each other. Door seals had to be redesigned for sound insulation and water resistance. The new windshield raised optical distortion concerns and affected the placement of sun visors and rear-view mirrors. It also required custom manufacturing methods for curvature and tinting. The new rear seats, though visually striking, took up more space than expected and created challenges for cargo capacity and rear ventilation routing. By the time the Model X entered beta prototype phase, it was clear the original 2014 delivery target would not be met. Tesla pushed the date back. Internally, resources had to be diverted from other programs. Production engineers who had just stabilized Model S assembly were now being asked to plan for a new, even more complex vehicle. Suppliers were being told to scale up parts that were still being redesigned. And unlike the Model S, which had launched in a more forgiving environment, the Model X was entering a market where expectations had changed. Tesla was no longer the new company with a big idea. It was now expected to deliver. By 2015, delays were mounting. The Falcon Wing doors were still unreliable in field testing. The seats remained a headache, difficult to assemble, prone to mechanical misalignment. The assembly process was not finalized, and the added weight of the vehicle compared to the Model S was beginning to impact real range estimates. Tesla decided to rebuild the production line in Fremont to accommodate Model X. It added new stations, new fixtures, and a second assembly flow that could produce both S and X models on parallel tracks. This meant pausing portions of Model S production for several days at a time to install new tooling. It also required retraining workers. The margin for error was narrowing. Throughout this, Elon Musk remained heavily involved. He insisted the Model X be delivered without compromises. He rejected proposals to simplify the rear doors. He refused suggestions to scale back the windshield. Even minor changes, like switching to conventional seats, were dismissed. Musk argued that engineering complexity would be justified by the long-term differentiation of the product. And so, the company pressed on. In September 2015, Tesla finally held its Model X delivery event. A small number of vehicles were handed over to early reservation holders. The event was celebratory but muted. Only a few dozen units were ready. Each had been hand-assembled. The production ramp was still tentative. Reviews were mixed. On one hand, the Model X was praised for its performance, especially the P9OD ludicrous variant, which could accelerate faster than most sports cars despite its weight. The ride was comfortable, the technology impressive, the interior quiet and futuristic. But early owners reported issues: doors that opened erratically, sensors that failed, seats that jammed, software bugs in the infotainment system, alignment problems with rear trim panels, rattles in the hatch, glitches in keyless entry. The issues were not widespread in every vehicle, but they were common enough to raise concerns. Tesla responded with updates. The over-the-air software infrastructure allowed engineers to push dozens of bug fixes within weeks. Adjustments were made to the Falcon wing logic. Service centers began installing mechanical updates. More training was provided to field technicians. Still, the Model X rollout was the most painful product launch Tesla had faced. Through the end of 2015 and into 2016, production remained slow. In some weeks, only a few hundred units were built. The added complexity made it harder to scale. Service centers struggled to keep up with repairs. Parts shortages persisted. The company learned a costly lesson. The Model X had become a study in over-engineering a vehicle whose unique features were impressive but carried hidden costs. Assembly times were longer, quality control was harder, supplier delays were more frequent, and profitability was limited. But there was an upside. By fighting through the Model X's challenges, Tesla built new internal muscles. It improved its ability to test and validate components. It expanded its in-house parts manufacturing. It gained deeper insight into the relationship between design, ambition, and operational capacity. And perhaps most importantly, the Model X experience reshaped Tesla's thinking for what would come next. The company began to prioritize manufacturability, because the next vehicle on the roadmap was not another premium product for a niche market. It was the centerpiece of Tesla's long-term strategy, an electric car for the masses, affordable, simple, scalable, the Model 3. By late 2015, Tesla was no longer a speculative startup. It had 2 production vehicles on the road. It was publicly traded. It had customers across multiple continents. It had earned a reputation for innovation, for risk-taking, and for ignoring traditional rules of the car business. But it had not yet proven it could become truly mainstream. That was the goal of the next vehicle internally. It was often referred to as the affordable Tesla. Externally, it was introduced to investors and the public as the Model 3. This name followed the loose naming convention Tesla had begun building: Roadster, Model S, Model X, The Model 3 would fill the gap in that sequence and, unofficially, complete the tongue-in-cheek spelling of the word SEXY. But unlike the other vehicles, the Model 3 was not designed to impress early adopters or car enthusiasts. It was meant to be a daily driver, a sedan for commuters, a car that would compete not with BMW or Mercedes, but with Toyota, Honda, and Ford. That goal came with three major challenges: price, scale, and simplicity. The Model 3 was promised at a starting price of $35,000 before incentives. This number was symbolic. It had been mentioned by Elon Musk for years. In an industry where electric cars typically started closer to $70,000, it represented a psychological threshold, a signal that electric mobility was no longer just for the wealthy. To reach that price, every component had to be examined. Designers began by rethinking the vehicle platform. While the Model S and Model X shared some components, the Model 3 would require an entirely new architecture. This new platform would be smaller, lighter, and cheaper to produce. The wheelbase was shortened. The number of motors per vehicle was reduced in base models. The battery pack used a different size of cell, moving from the older 18,650 form factor to the new 2,170 cells. Developed in partnership with Panasonic, the 2,170 cell was more energy dense, more thermally efficient, and designed specifically for high-volume manufacturing. Tesla planned to build these cells at its new Gigafactory in Nevada at the time. The Gigafactory was still under construction, a vast facility near Reno, designed to be one of the largest buildings in the world. By footprint, it would eventually produce battery cells, modules, and powertrain components. But in 2015, it was still concrete, wiring, HVAC ductwork, and construction noise. Even so, the Model 3 engineering team began planning as if the cells would be ready. The car's structure had to be compatible with these new battery modules. New cooling loops were developed. New software controls were written. Engineers tested early battery pack designs using simulated load profiles. Everything had to be both cost-effective and durable. Then came the challenge of simplifying the interior. Tesla wanted the Model 3 to have the same futuristic feel as the Model S, but with far fewer components. The decision was made to remove the instrument cluster entirely. No traditional speedometer, no gauge cluster. Instead, everything, speed, range, navigation, climate controls, would be shown on a single, central 15-inch touchscreen. This was controversial internally. Some engineers and executives worried that customers would find it disorienting. Others argued it reduced parts cost and created a minimalist feel that aligned with Tesla's design ethos. After debate and prototyping, the touchscreen-only layout was finalized. The steering wheel was simplified. Most physical buttons were removed. Air vents were replaced with a hidden HVAC system that allowed air to flow through a continuous slit along the dashboard, controlled entirely by touchscreen input. It was clean, modern, less expensive to manufacture at scale, but also reliant on software that would need to function without fail. The drive controls were rethought too. No start button. The car would detect the driver's presence and activate when the brake pedal was pressed. Gear selection was handled by a stalk. Everything from phone pairing to seat adjustments was stored in the driver profile, tied to the key fob or phone. Each of these decisions reduced the number of individual parts, but it made the car software-dependent, and that meant Tesla would have to commit to building and maintaining a massive codebase, not just for navigation and entertainment, but for climate control, vehicle access, charging behavior, regenerative braking profiles, and touchscreen responsiveness. As the design firmed up, manufacturing planning began. This was the most ambitious part of the project. Tesla would need to build hundreds of thousands of Model 3 units per year. That meant purchasing new stamping presses, expanding the Fremont plant, designing new production lines, and training a new wave of factory workers. Musk famously claimed that the factory itself would become the product, more advanced and efficient than the vehicles it produced. He referred to this idea as the machine that builds the machine. Tesla began to invest heavily in automation. Robotic arms were ordered from KUKA, conveyors were installed. Software engineers were brought in to write the logic that would govern robotic welders, material handling bots, and assembly sequences. Musk envisioned a line that could run nearly autonomously, minimizing labor costs and maximizing precision. It was bold, but it also meant Tesla would be trying to solve vehicle engineering and factory automation at the same time. That overlap created friction. Mechanical engineers were waiting for automation specs to finalize part shapes. Factory designers were waiting for vehicle teams to confirm component dimensions. Bottlenecks emerged long before the first vehicle had even been built. Meanwhile, the public announcement loomed. Tesla had scheduled a Model 3 unveiling event for March 31, 2016. The vehicle was not yet finalized, but the company wanted to show a working prototype and begin accepting reservations. In preparation, Tesla built a small batch of alpha prototypes. These were not full production vehicles. They were design studies, with many components hand-finished, but they were functional enough to drive on stage, take test laps in the parking lot, and demonstrate the car's size, layout, and interface. The event was a success. Thousands of people stood in line to reserve the car. Online systems were flooded with pre-orders. Within the first week, Tesla had received over 325,000 reservations, each backed by a refundable deposit. No one had seen final specifications. No one knew the exact delivery date, but the trust in Tesla and the hunger for an affordable electric car was strong internally. This surge of demand created pressure. Tesla now had a list of hundreds of thousands of customers waiting for a car that did not yet exist in finished form. The expectations were set. The timelines were aggressive. The capital required was enormous. Every department was pushed into motion. Procurement began locking down suppliers. Construction crews worked overtime to expand Fremont. Engineers raced to finalize hardware. The Gigafactory was accelerated to meet battery needs. Robots arrived in crates and had to be installed, tested, and programmed, and with every passing week, the stakes grew. The Model 3 was not just a product, it was a test of Tesla's ability to become what it had always claimed it would be, a real car company at scale. The goal was clear: take a design meant for mass appeal and produce it at a scale Tesla had never achieved before. The Model 3 was supposed to mark the company's transition from niche automaker to high-volume global competitor. The pressure started building before the first production vehicle even rolled off the line. By mid-2017, the Model 3 was still in pre-production testing. Early units were being assembled in extremely low numbers, mostly by hand, so that teams could confirm part fitment, work out kinks in the software, and begin durability testing under controlled conditions. These units were not sold to the public. They were often taken apart after road testing and inspected for signs of wear, corrosion, or structural stress. But the real challenge wasn't building a few dozen hand-finished test vehicles. It was building 5,000 cars per week. That was the figure Tesla had promised. It was an ambitious rate, one that would mean producing more cars in a month than the company had ever delivered in an entire year before. And it required that every part of the Fremont factory, stamping, body welding, paint, general assembly, software upload, and quality inspection, run continuously, in perfect coordination. Tesla had leaned heavily into automation to achieve this. Elon Musk had championed the idea that robots, not humans, should be responsible for the bulk of assembly work. This included not just welding or painting, which were already robot-heavy, but even tasks like wiring harness installation, parts delivery, and trim application. Tesla ordered dozens of robots from KUKA and Fanuc, top industrial automation companies. These machines were installed in new sections of the Fremont plant, which had been cleared, reconfigured, and rebuilt to accommodate the Model 3 line. Tesla engineers began integrating custom software to govern these robots, writing code that would control movement sequences down to the millimeter. But almost immediately, things began to break down. Many of the robots were unreliable when operating at speed. Some were too slow, others required constant recalibration. In one case, an automated parts feeder jammed so often that workers had to babysit it full-time, defeating its purpose. In another, a robot designed to install interior trim panels applied too much force and damaged the parts. These were not isolated incidents. They were symptoms of a much larger issue. Tesla had tried to automate processes that were not ready to be automated. Traditional automakers had learned through decades of trial and error that automation works best when it supports repetitive, constrained motions, welding body panels, applying paint, lifting heavy assemblies. But for more delicate, variable tasks, like routing wiring, aligning seals, or attaching soft trim, human workers were still more efficient and adaptable. Tesla had ignored that lesson, and so, production slowed to a crawl. By Q3 2017, Tesla was delivering just 260 Model 3 South, far below its projected targets. Publicly, the company blamed bottlenecks in the battery module assembly at the Gigafactory in Nevada. Internally, there were dozens of other issues: robotic coordination problems, supply chain hiccups, software integration bugs, and unfinished factory systems. Executives were now in crisis mode. Elon Musk began sleeping at the Fremont factory, sometimes in a conference room, other times on a couch. He personally oversaw production meetings, often late into the night. Whiteboards were filled with flowcharts, teams were reassigned, engineers were pulled from other projects to fix line issues. A system designed for 80% automation was now seeing human workers stepping in to do what the machines could not. In one instance, Tesla scrapped an entire robotic conveyor section and replaced it with manual cart systems, pushed by workers wearing orange safety vests. In another, a sub-assembly line was relocated to a nearby warehouse, and Model 3 components were ferried back and forth by truck. Then came one of the most symbolic moments of this period: the construction of a tent in mid-2018, with deadlines looming and internal capacity maxed out. Tesla erected a massive tented structure outside the Fremont facility, officially called GA for General Assembly. For it housed an additional Model 3 assembly line built largely from spare parts and manually run. Critics mocked the decision. A car company using a tent to build vehicles was seen as desperate, even amateurish. But it worked. Tesla began assembling hundreds of Model 3 units per day inside the structure. The process was rough. Ergonomics were poor. Conditions were noisy and hot, but output increased. By June 2018, Tesla hit its long-promised milestone, 5,000 Model 3 South in 1 week. The number was real, though just barely. It had required a full-court press, extra shifts, overtime, unorthodox workflows, but it proved that the car could be built at volume. Still, the road had been bruising. Employees spoke of burnout. Some worked 12-hour shifts, 6 days a week. The learning curve was steep, and the pressure to keep the line moving was relentless. Managers tracked every minute of downtime. Supplies were expedited at massive cost, and the financial picture remained precarious. Tesla was spending billions. The Model 3 project had consumed huge amounts of capital, and profitability remained elusive. Analysts questioned whether Tesla could sustain these build rates without running out of money. Yet something else was happening at the same time. Customers were taking delivery. Model 3 South began appearing on roads across the United States. Online reviews circulated. Enthusiasts posted videos of their deliveries. The car's combination of performance, minimalism, and high-tech features appealed to a younger, tech-savvy demographic. Supercharging access made long-distance travel possible. The vehicle's software was updated weekly with improvements and bug fixes. Demand stayed high. The company introduced new variants. The long-range model with a larger battery and premium interior. The performance model with upgraded motors and suspension, and eventually the Standard Range Plus, which brought the vehicle closer to the original $35,000 price point. Tesla managed to shrink the Model 3's production cost over time. Part of this came from simplifying options, fewer paint colors, standardized interiors, bundled features. Part came from retooling lines, renegotiating supplier contracts, and improving battery module yields at the GIGA factory. By the end of 2018, Tesla had not only stabilized production, it had achieved something more rare: a profitable quarter. The company posted positive net income in Q3 2018, driven largely by Model 3 sales. Wall Street took notice. Tesla's stock recovered. Skepticism faded, if only briefly. And inside the company, the mood shifted. Model 3 had brought Tesla to the edge of collapse, but it had also saved it. What remained now was the task of scaling even further, because demand was global, and the world was waiting. By the end of 2018, Tesla had survived the Model 3 ramp. Production had stabilized, deliveries were growing. Investors were cautiously optimistic, but Elon Musk and Tesla's leadership knew that the next chapter could not simply be about delivering cars in California or the East Coast. To justify its valuation and mission, Tesla had to become a true global automaker, and to do that, it needed to go where the demand was and where the factories were not. China was the obvious first target, not just because of its enormous population or rapid EV adoption, but because China was already the largest automotive market in the world. More cars were sold in China each year than in the United States and much of Europe combined. The Chinese government had also signaled a strong national interest in electric vehicles. EV buyers could get license plate exemptions, tax breaks, and easier access to urban vehicle registration, especially in cities like Shanghai, Beijing, and Shenzhen. Tesla had been selling vehicles in China since 2014, but only through exports. Cars were built in Fremont, shipped across the Pacific, and delivered to Chinese customers weeks later, an expensive and logistically complex operation. Import tariffs alone could add more than 25% to the cost of a vehicle. This made Tesla's a luxury product, inaccessible to most middle-class buyers. The solution was obvious. Build cars in China, but foreign companies had traditionally been required to enter joint ventures with local firms to manufacture in China. These arrangements often included intellectual property sharing, state involvement, and diluted control. Tesla wanted something different, and in 2018, it got it. After negotiations between Tesla and Chinese authorities, helped in part by China's shifting stance on foreign investment, Tesla became the first foreign automaker allowed to own a factory outright in China. No joint venture, no Chinese partner, full control. The agreement included a deal to build the factory in Lingang, a development zone on the outskirts of Shanghai. In return, Tesla would be expected to contribute to the local economy, source some components locally, and support job creation. Construction on Gigafactory Shanghai began almost immediately in January 2019. The speed of progress shocked many in the industry. Within just 10 months, the main structure was standing. Concrete, steel beams, wiring, ventilation, painting bays, stamping presses, all brought in, assembled, and commissioned with a level of speed that few Western projects could match. By late 2019, trial production had already begun. This factory was different in one key respect. It would produce the Model 3, specifically for the Chinese market. That meant adapting to local standards, Chinese electrical systems, local supplier constraints, different regulatory compliance. Tesla had to localize not only the language in its software, but also the service and repair ecosystem. Customer support teams were hired and trained. Charging infrastructure had to be rapidly deployed, both superchargers and home charger installations. At the same time, Tesla expanded its retail presence in Chinese malls and shopping centers. Stores were opened in high-traffic urban areas. Test drives were offered. The Model 3 began appearing not as a foreign novelty, but as an increasingly common choice for tech-savvy, status-conscious buyers. By early 2020, just over a year after groundbreaking, Tesla began delivering Shanghai-built Model 3 units to customers. The price was lower, delivery times were shorter, and Chinese buyers responded. Demand surged. It wasn't just about prestige anymore. The car was priced competitively against local offerings. Government incentives remained in place, and Tesla's branding as a clean, tech-forward company resonated with younger drivers. Meanwhile, Tesla also had its eye on Europe. European demand for the Model 3 had been strong since its initial availability. In countries like Norway and the Netherlands, EV adoption was already advanced, driven by incentives and environmental goals. Tesla had set up a final assembly point in Tilburg, Netherlands, where vehicles shipped from the US were completed for European delivery. But the process was still expensive and slow. In 2019, Tesla began planning its next major expansion, a full-scale factory in Germany. The project was dubbed Gigafactory Berlin-Brandenburg, or simply Giga Berlin. The site would eventually produce not just the Model 3, but also the upcoming Model Y. Tesla's compact crossover designed for high-volume European sales. Germany was a symbolic choice. It was the heart of the traditional automotive industry, home to Volkswagen, BMW, Audi, and Mercedes-Benz. By choosing to build in Germany, Tesla was signaling that it would compete head-to-head on their home turf. But the Berlin project quickly ran into challenges. Environmental approvals delayed the site. Construction was paused due to concerns over water usage, wildlife disruption, and local protests. Tesla was forced to revise its plans, conduct additional impact assessments, and engage more deeply with local stakeholders. Despite these delays, Tesla moved forward. The plan for Giga Berlin included advanced paint shops, next-generation stamping presses, and the ability to build both battery cells and full vehicle assemblies on-site. Recruitment for local engineers, factory workers, and supply chain staff began even before the main structures were complete. Back in Fremont, the focus remained on maximizing Model 3 production for global delivery. Logistically, this meant Tesla was now running a three-continent supply chain. Fremont supplied North America and some Europe. Shanghai supplied China and began exporting to nearby Asian markets. Berlin, once operational, would handle most European demand. This level of coordination required a massive back-end system. Tesla had to monitor part availability, production rates, shipping timelines, customs clearance, regional regulatory compliance, and customer delivery scheduling, all from a centralized network of systems that tracked vehicles from initial VIN assignment to final HANDOFF. And yet, even with all this complexity, the vehicles kept shipping. By the end of 2020, Tesla had delivered nearly 500,000 vehicles, its highest annual total to date. The majority of these were Model 3 South. The car had become Tesla's workhorse, the financial backbone. It was the vehicle that made Gigafactory Shanghai possible, the one that gave Tesla leverage to negotiate in Europe, the one that brought Tesla from the brink of collapse into consistent quarterly profits. And the story wasn't over, because Tesla was already planning the next steps: a vehicle for even lower price points, energy products to support its EV ecosystem, and eventually a pickup truck that would defy every design convention in the industry. But first, there was one more model to launch, one based on everything Tesla had learned from the Model 3, the Model Y. The Model Y was not born out of drama. It was not unveiled with secret prototypes hidden under cloths or promised with radical reinvention. Unlike the Roadster, the Model S, or even the Model 3, there was no breathless fanfare when it was first announced. It was revealed in March 2019 at a modest, almost subdued event in Hawthorne, California, next to Tesla's design studio, and yet, over the next few years, it would quietly become one of the most important vehicles in Tesla's entire lineup. The Model Y was a crossover SUV built on the same platform as the Model 3. It shared approximately 70% of its parts with the Model 3, including the battery packs, electric motors, and much of the underlying software architecture from the start. This was the plan. Tesla had learned a difficult lesson during the launch of the Model X: complexity, novelty, and over-engineering made for slow production, high costs, and strained service operations. With the Model Y, the goal was very different. It was to scale easily, to launch smoothly, and to become a global volume vehicle without disrupting Tesla's now delicate manufacturing rhythm. Inside, the Model Y looked almost identical to the Model 3. The same minimalist dashboard, the same center-mounted 15-inch touchscreen, the same steering wheel, software menus, and interface behavior. It offered more cargo space, a slightly higher seating position, and optional third-row seats to push it into the small family SUV category. But these changes were subtle, measured, and intentional. Tesla engineers designed the Model Y from the start to be easier to build. The structure included fewer unique parts, simplified wiring harnesses, and consolidated systems. Even the rear hatch, a traditional problem area for noise, water leakage, and alignment was designed with early lessons from the Model X's overly complex liftgate system in mind. The vehicle's body was also an opportunity for Tesla to experiment with its next major manufacturing innovation, the gigacasting process. Gigacasting referred to the use of extremely large aluminum castings to replace many smaller parts in the vehicle's chassis. Traditionally, an automotive underbody might be made up of dozens or even hundreds of welded steel components. With gigacasting, Tesla began replacing entire sections of the vehicle's rear underbody with a single cast aluminum piece. This offered major advantages. Fewer parts meant fewer welds, fewer robots, and less time on the production line. It also reduced weight, increased rigidity, and simplified quality control. Tesla partnered with IDRA, an Italian casting machine manufacturer, to design and build these enormous casting presses, machines larger than a delivery truck, capable of injecting molten aluminum into high-pressure molds with extreme precision. The first applications of this technology appeared in early versions of the Model Y. Over time, Tesla began expanding the use of castings in other structural areas of the vehicle. Eventually, it would form a core part of the company's long-term manufacturing philosophy. Build the car like you build a toy, with as few pieces as possible. Tesla launched the Model Y in the United States in early 2020, just as the world was entering the grip of the COVID-19 pandemic. The timing was chaotic. Production began in Fremont. Initial deliveries focused on the long-range all-wheel drive variant. The line had been adapted from the Model 3 line, making it one of Tesla's fastest and smoothest product ramp-ups. The Model Y rollout stood in contrast to the painful birth of the Model 3. There were fewer surprises, fewer public setbacks, and fewer complaints. But the pandemic created new obstacles. Tesla was forced to shut down its Fremont factory in March 2020 under local public health orders. Deliveries halted, employees were sent home. The factory floor went quiet. For several weeks, Tesla's operations were frozen. But unlike many traditional automakers, Tesla was able to pivot quickly because it controlled its sales process directly. With no independent dealership network, Tesla began experimenting with contactless delivery, remote paperwork, and digital coordination. Customers could purchase and take delivery with minimal in-person interaction. By mid-2020, Model Y production resumed, and demand was strong. The market had shifted. More people were seeking crossovers and SUVs than sedans. The higher ride height, roomier cargo space, and improved road visibility of the Model Y made it a practical choice. Families saw it as a better alternative to the Model 3. The supercharging network had expanded. Home charging had become more mainstream, and tax credits in some regions still applied. Tesla soon began preparing to expand Model Y production beyond California. In Shanghai, the Gigafactory had already begun building Model 3 units. Tesla now modified the site to accommodate Model Y assembly lines, aiming for local production to feed not just China, but potentially other parts of Asia as well. The first Model Y units built in Shanghai were delivered in early 2021. At the same time, in Berlin, construction was underway for what would become Tesla's primary European hub for both Model Y and future vehicles. The Giga Berlin facility faced delays, regulatory reviews, and local protests, but eventually, the groundwork was laid for Model Y production to begin there as well. And in Texas, a new Gigafactory was rising. Giga Texas, located near Austin, was conceived as a multi-purpose facility. Vehicle production, battery cell manufacturing, and advanced casting operations. Tesla planned to build the Model Y here using the latest manufacturing techniques, including structural battery packs, in which the battery itself becomes part of the car's load-bearing structure, reducing weight and complexity even further. With each location, Tesla refined the Model Y assembly process. The car was not flashy. It had no Falcon wing doors, no record-breaking acceleration numbers, no conceptual gimmicks. But it was exactly what the company needed: a scalable, reliable, efficient vehicle that could be sold in huge volumes around the world. By the end of 2021, the Model Y had become one of Tesla's best-selling vehicles. In fact, in some quarters, it outsold the Model 3. It offered better margins, fewer assembly complications, and broader appeal. In a market where crossovers dominated, Tesla had quietly inserted itself into the mainstream, not just among early adopters or EV enthusiasts, but among everyday buyers. The Model Y also began to replace the Model 3 as the company's platform for innovation. It was used to trial new battery pack formats, new motor assemblies, and new manufacturing strategies. And over time, its consistent sales helped fund the next round of Tesla projects, including energy storage, software development, and a long-teased new vehicle, the Cybertruck. But that's a story still in the making. The Model Y, meanwhile, rolled on, often unnoticed, rarely celebrated, but carrying Tesla forward with every mile. By the time the Model Y had established itself as a core product in Tesla's lineup, the company was no longer viewed solely as an automaker. Analysts, investors, and the media had begun to shift their language. Tesla was now often described as a technology company or an energy company, depending on the focus of the conversation. This was not a sudden transformation, but rather the result of a parallel vision that Elon Musk had been promoting for more than a decade. A vision that extended far beyond electric vehicles. The idea was simple in concept, but difficult in execution. Tesla would not just produce the machines that consumed energy, it would also produce the systems that generated, stored, and managed it. Cars were only the entry point, the most visible and emotionally compelling piece of the puzzle, but behind them sat an entire infrastructure challenge, one that required batteries, software, and solar technology to work together in seamless coordination. The seeds of this broader energy strategy had been planted. Years earlier, in 2016, Tesla acquired a company called SolarCity, founded by Lyndon and Peter Rive, Elon Musk's cousins. At the time, SolarCity was one of the largest residential solar providers in the United States, offering rooftop solar panel installation and long-term financing. The acquisition was controversial. Critics called it a bailout. Tesla shareholders were skeptical. Musk defended the move by calling it a natural extension of Tesla's mission to accelerate the transition to sustainable energy. With the acquisition complete, Tesla began to integrate solar into its product ecosystem. This included rebranding SolarCity's services under the Tesla name and streamlining offerings. The flagship concept was a package that would eventually include solar panels, a home battery called the Powerwall, and Tesla vehicles, all controlled via a central app. The idea was that a homeowner could generate their own electricity, store excess energy for use at night or during grid outages, and use that energy to power their vehicle. At the center of this system was the Powerwall. The Powerwall was a lithium-ion battery pack designed for home energy storage. First introduced in 2015 and refined over multiple generations, it allowed homes with solar panels to retain energy instead of sending it back to the grid. It also served as a backup power source during outages. The Powerwall was wall-mounted, relatively compact, and paired with an intelligent energy management system that could forecast usage, charge patterns, and weather conditions, that Powerwall was not just about convenience, it was about grid independence in regions with unreliable utilities or frequent natural disasters. The Powerwall became a lifeline. In California, where wildfires and planned blackouts disrupted electricity service, Tesla saw a surge in demand. The Powerwall's software could even be updated over the air, improving performance or adding features like Storm Watch mode, which prioritized charging when severe weather was forecast. Then there was the PowerPack and Megapack, Tesla's commercial and utility-scale energy storage solutions. PowerPack units were deployed at businesses, data centers, and remote installations. They helped reduce peak demand charges and provided stability in areas with grid instability. The Megapack, introduced later, was designed for large-scale energy projects. It consisted of a container-sized battery system capable of storing up to 3 megawatt-hours of energy. Tesla deployed Megapack installations across the world, from South Australia, where it helped stabilize the grid during peak loads, to the United Kingdom, Hawaii, and parts of California. These projects were not just demonstrations. They were revenue-generating infrastructure investments. Tesla had entered the energy utility business quietly, but meaningfully. But while solar and batteries addressed generation and storage, there was still one more critical element: software. Tesla had long used software to update its vehicles. Over-the-air updates allowed for improvements in driving dynamics, battery management, user interface design, and even entirely new features like Sentry Mode, Dog Mode, or the infamous Fart app. But in parallel, Tesla was building a much more ambitious software platform, one that touched every part of the user experience. This included the Tesla mobile app, which allowed owners to check vehicle status, initiate charging, precondition the cabin, and even summon the car from a parking space. It also included navigation software, which integrated real-time traffic data, charging stop planning, and automatic rerouting. Tesla's approach to software was fundamentally different from legacy automakers. Instead of outsourcing these functions, Tesla developed them in-house and deployed improvements continuously. The most ambitious part of Tesla's software effort, however, was Autopilot. Initially launched as a driver assistance package, Autopilot enabled adaptive cruise control, lane centering, and basic self-steering on highways. The system used a combination of cameras, ultrasonic sensors, radar in earlier models, and eventually Tesla designed chips to process driving data in real time. Over time, Tesla introduced an expanded version called Full Self-Driving FSD, a package that promised, eventually, to allow for hands-free, point-to-point autonomous driving. It included traffic light recognition, automatic lane changes, on-ramp to off-ramp navigation, and more, but the rollout was cautious. Tesla used a small group of testers to train the system and improve behavior. The software remained in beta, and the company warned that drivers must remain attentive at all times. Despite criticism from regulators and competitors, Tesla maintained that FSD would improve over time with data. Every Tesla vehicle on the road became a rolling data collection unit. Tesla amassed billions of miles of driving data: corner cases, pedestrian behavior, lane merges, unprotected left turns. This information fed into the company's neural network training systems, which continually refined the vehicle's behavior. The integration of hardware, software, and energy systems created a kind of Tesla ecosystem, one that few other companies could replicate. A customer could own solar panels, a Powerwall, a Tesla vehicle, and manage everything through a single app. The same update infrastructure that improved battery performance in a car could also be used to add new features to a home energy system. This ecosystem gave Tesla another edge. Brand stickiness. Owners who bought into one product were more likely to purchase others. A Model 3 driver might become a solar customer. A solar customer might add a Powerwall owner might upgrade to a Model Y. Each product reinforced the value of the others. By 2022, Tesla's energy division was no longer a speculative side project. It was growing, quietly, deliberately, and consistently profitable. And the software stack that underpinned it all, from autopilot to energy management, was increasingly becoming Tesla's moat. Traditional automakers were still shipping vehicles with fragmented infotainment systems and third-party navigation software. Tesla controlled the stack, the data, and the user experience. But software and batteries were only part of the future Tesla envisioned, because one project remained that promised to change not just how vehicles were built, but what they looked like. The Cybertruck. When Tesla unveiled the Cybertruck in November 2019, it did not resemble any other vehicle on the road. It did not even resemble previous Tesla models. Gone were the smooth curves and flowing panels of the Model S or Model 3. In their place stood a rigid polygon, a matte grey wedge of steel and glass that looked more like a vehicle from a dystopian video game than a suburban driveway. The reveal event took place in Los Angeles, in the same space used for the semi-truck unveiling. It began with a light show, dramatic music, and a video montage of rugged driving through deserts and test tracks. When the Cybertruck rolled on stage, the audience's reaction was one of confusion, laughter, and surprise. The truck had no paint. Its body panels were flat, angular, and raw. Its frame was made of cold, rolled stainless steel, a material so hard that traditional stamping presses could not shape it. Instead of aluminum or carbon fiber, Tesla had chosen ultra-hard 30X stainless steel, the same alloy Elon Musk claimed was used in SpaceX rockets. This choice was driven in part by durability goals. The material would not dent easily, and it would resist corrosion. But there were consequences. Using stainless steel meant Tesla had to abandon conventional manufacturing techniques. The metal was too hard for normal automotive presses. It required a redesign of panel joining techniques. Welding stainless steel at scale, with repeatable precision and without distortion, presented a new set of engineering challenges. Body tolerances were tighter. Reflections on the raw metal created difficulties for visual inspection, and the rigidity of the panels left little room for adjustment. The Cybertruck's windows were also designed for durability. Tesla called them armor glass. During the reveal, a steel ball was thrown at the driver's window in what was intended to be a live demonstration of the material's strength. The window cracked immediately. Then the second window cracked as well. Elon Musk laughed awkwardly. The demo had not gone to plan. Yet. Despite the failed demonstration and the radical design, pre-orders began to pour in. Within days, Tesla announced that over 250,000 reservations had been made, each with a fully refundable $100 deposit. The interest came not just from existing Tesla fans, but from pickup truck owners curious about something new, and from those drawn to the spectacle and boldness of the design. The Cybertruck was promised in 3 variants: a single-motor rear-wheel drive with 250 miles of range, a dual-motor all-wheel drive with 300 miles of range, and a tri-motor all-wheel drive version with over 500 miles of range and a claimed 0 to 60 time of 2.9 seconds. The vehicle would feature adaptive air suspension, an onboard 120 volts and 240 volts power outlet, and even the capability to operate as a portable generator for job sites or emergencies. The rear bed was covered by a motorized roll-top tonneau cover, and the vehicle would include a built-in ramp for loading motorcycles or ATVs. Initial pricing started at $39,900. It was aggressive, almost too aggressive. Industry observers questioned whether Tesla could build such a vehicle at that price, especially with its unorthodox materials, massive battery requirements, and production challenges. But as with previous Tesla launches, the goal was to capture attention, collect pre-orders, and begin the slow process of turning a concept into a shipping product. Tesla planned to manufacture the Cybertruck at a new facility in Texas, dubbed Giga Texas or Gigafactory Austin. This site would become the largest Tesla manufacturing site in the United States. The location was chosen for a mix of regulatory friendliness, tax incentives, and central geography. The land was acquired in 2020, and construction began quickly. Gigafactory Austin was designed not just to build Cybertrucks, but also to produce the Model Y, battery cells, and later vehicles. Inside the Texas facility, Tesla began developing a new kind of assembly line. The Cybertruck's unique materials meant it could not simply be built on a modified Model 3 or Model Y line. Everything from material handling to robotic arms had to be customized for the truck's size and rigidity. Meanwhile, Tesla engineers worked to solve the Cybertruck's toughest design challenges. The windshield wiper, for example, proved difficult. The massive flat glass surface required an unusually large wiper blade, one that could not easily be hidden under the hood. The truck's angular body panels made crash compliance complex. Pedestrian safety requirements in Europe posed additional design limitations. Even small details like side mirrors, lighting elements, and bumper compliance had to be reimagined. Then came the delay announcements. Originally, Tesla had targeted production in late 2021, but as 2021 turned to 2022, timelines slipped. Supply chain issues, particularly around semiconductors and materials, added to the delay. Tesla also wanted to introduce its 4,680 battery cells in the Cybertruck, a next-generation format with improved energy density, lower cost, and simplified structural integration. These new cells were not yet in mass production. Tesla continued building prototypes. Sightings of test vehicles circulated online, sometimes driving on highways, sometimes parked at charging stations. The design had been modified, the size reduced slightly, the mirrors were made removable. Interior screens and user interface elements were taken from the Model S refresh, but mass production remained elusive. Despite this, demand remained high. By 2023, Tesla had logged over 1 million reservations for the Cybertruck. The vehicle had become a kind of status symbol, even before it existed. Celebrities posed with pre-production units. Social media filled with renders and speculation. Some competitors accelerated their own electric truck programs, including Ford's F-150 Lightning, Rivian's R1T, and Chevrolet's Silverado EV. The Cybertruck's real influence was symbolic. It pushed the boundary of what an electric vehicle could look like. It attracted attention to the entire category. It gave Tesla a foothold in the lucrative truck market, a segment traditionally dominated by American legacy brands. And even though it was years behind schedule, it served a purpose, keeping Tesla at the forefront of public conversation. By late 2023, Tesla announced it would begin deliveries in 2024, starting with limited volume and gradually ramping up as the Texas factory reached higher output. The Cybertruck, like the Roadster before it, was more than just a product. It was a statement that Tesla was still willing to take risks, that it would not retreat to conservative design, that it saw itself not just as a car company, but as a cultural force, shaping expectations and aesthetics in ways no other automaker attempted. But it also reminded Tesla of something familiar, that turning bold ideas into physical products always took longer, cost more, and introduced new complexity. And yet, Tesla kept building, because the next challenge was already in view: a more affordable car, a global platform, and a future that would rely not just on cars, but on robots. By the middle of the 2020s, Tesla stood at a strange and unprecedented crossroads. It was no longer the upstart disruptor. It was no longer the scrappy underdog facing bankruptcy and building cars under tents. Tesla had become, in market value and cultural recognition, one of the most important companies in the world. Yet, for all the progress it had made, gigafactories on 3 continents, hundreds of thousands of vehicles delivered each quarter, an expanding energy division, and a loyal customer base, there remained an open question at the heart of its story. What, exactly, was Tesla becoming? The question was more than branding. It spoke to the company's evolving identity. Was Tesla a car company, a battery manufacturer, a software platform, an energy utility, a robotics firm? Elon Musk suggested that it was all of those things, and something more. At the core of Tesla's next decade was a plan that revolved around scale, autonomy, and artificial intelligence. Tesla's vehicles were still relatively expensive. Even the base Model 3 and Model Y, despite reductions over time, remained out of reach for large portions of the global population. To truly fulfill its mission, accelerating the world's transition to sustainable energy, Tesla needed to build a smaller, more affordable car. Internally, this was often referred to as the next generation platform, or sometimes the Model 2, though Tesla never officially named it. The goal was to design a vehicle that could be sold globally at a price point around $25,000. This would involve rethinking the entire vehicle architecture, from the way the battery pack was assembled to the layout of seats, controls, and electronics. Tesla had already made progress. The 4,680 battery cells, with their simplified structure and improved manufacturing yield, were a key enabler. So were the Gigok castings, which replaced dozens of parts with just a few massive components. The idea was not just to build a cheaper car, but to build it more efficiently, with a smaller factory footprint, fewer labor hours, and reduced complexity. Giga Texas and Giga Mexico were slated to be the primary production sites for this new platform. Tesla teased some of its architecture at investor events, showing minimalist underbody frames and modular battery packs, but the full vehicle design remained under wraps. The production timeline was flexible. Some said 2025, others expected delays. But the strategy was clear. Tesla needed to sell millions of these smaller vehicles to compete globally and make EVs accessible to more markets, including India, Southeast Asia, and parts of South America. It would also allow Tesla to tap into urban markets where compact size, not acceleration, was the selling point. But scaling production was only part of the vision. The other part involved removing the driver entirely. Tesla's self-driving program, long the subject of both hope and skepticism, remained one of its most ambitious efforts. The company had chosen a path unlike nearly every other autonomous vehicle developer. While competitors relied on high-definition maps, LiDAR sensors, and carefully geofenced environments, Tesla focused on pure vision, training its cars to see and understand the world using only cameras and artificial intelligence. Tesla built a massive computing cluster to support this goal. It called the training supercomputer Dojo, a custom-built system designed to process video data and train neural networks faster than conventional systems. The company used billions of real-world driving miles collected from its fleet to improve decision-making, edge case handling, and prediction accuracy. The system was rolled out in stages. First came autopilot highway steering, adaptive cruise control, and automatic lane changes. Then Navigate on autopilot, which could guide a car through highway interchanges and off-dash ramps. Then full self-driving beta, which expanded functionality to city streets, stop signs, roundabouts, unprotected left turns, and more. But full self-driving remained a driver assist feature, not full autonomy. Drivers had to stay alert, hands on the wheel, eyes on the road. The system could make mistakes, and Tesla made that clear. Still, the company believed that with enough data, enough compute, and enough refinement, it would eventually cross the threshold into full automation. It was not just about convenience. Elon Musk envisioned a world where Tesla vehicles could become robotaxis, summoned by an app, operating with no human driver, generating passive income for owners, and reducing the cost of transport. It would redefine urban mobility. It would reduce congestion. It would eliminate the idle time most vehicles spend parked. It was a grand idea. It was also extremely difficult. By the mid-2020s, no company had yet achieved full Level 5 autonomy at scale. Tesla remained confident that its approach, software first, hardware aligned, data rich, would get there first. Yet, autonomy was only one part of the broader vision, because behind the cars, the batteries, and the energy systems, Tesla had begun building something more speculative. In 2021, at Tesla's AI Day presentation, Elon Musk revealed a new project, Optimus, also referred to as TeslaBot. It was a humanoid robot designed to perform repetitive or dangerous tasks. Tesla framed the bot as a general-purpose machine capable of walking, lifting objects, using tools, and eventually operating in human-designed environments like homes, factories, and warehouses. Skeptics rolled their eyes. Humanoid robots were a staple of science fiction and an ongoing challenge in robotics. Balance, motion control, task recognition. These were problems that academic and industrial researchers had been working on for decades. Tesla had no background in this field, but Musk argued that Tesla was well positioned. The company already had deep expertise in AI, real-time decision-making, hardware integration, and power-efficient systems. Tesla's vehicles were robots on wheels. The same neural networks that allowed a car to drive could, in theory, allow a robot to navigate the world in the years that followed. Tesla showed early Optimus prototypes, walking slowly, lifting boxes, and manipulating small objects. The robots were crude compared to the final vision, but the company framed it as a long-term investment, one that, if successful, could redefine labor in the same way the Model S redefined electric performance. Tesla said that one day Optimus could cost less than a car, that it could be used in homes, elder care, factories, or agriculture, that it could take on the dull, dangerous, or dirty jobs humans avoided. The dream was enormous. The path there was uncertain, but Tesla was serious about pursuing it, because for all its ambition in vehicles, The company seemed increasingly driven by a desire to create a vertically integrated future where energy, mobility, intelligence, and labor were part of the same ecosystem. A Tesla home with solar panels and Powerwall storage, a Tesla vehicle with autonomy and full connectivity, a Tesla robot assisting with groceries or deliveries, all coordinated by a centralized AI system, all updating over the air, all designed to improve with time. It was futuristic. It was far from guaranteed, but it was Tesla's vision. As the story of Tesla reaches its current point, the contrast with its origins is hard to ignore. It began as a small group of engineers and entrepreneurs trying to prove that electric vehicles could be cool. It survived near bankruptcy, production delays, public scrutiny, lawsuits, and leadership turnover. It scaled from a hand-built sports car to a global manufacturing network delivering over 1 million vehicles per year. And it still moves forward, sometimes confidently, sometimes chaotically, but always forward. In the background, the company continues to iterate on battery chemistry, on software stacks, on factory design, on supply chains, on vehicle control systems, on machine learning pipelines, on hardware optimizations. It is part automaker, part software firm, part energy company, and part something that does not yet have a clear name. It is not perfect. There are recalls, delays, controversies, and moments of confusion. But Tesla remains, above all, a company that does not stand still. And perhaps that is what has allowed it, against the odds, to become not just a car company, but a tech empire.